Okay. Oh.
It's fine. It's conformity.
Yeah, I should have done it better. Right. So, can someone bring more chalk, actually? These are all tiny pieces. Um, oh. Why do you have this? Wow. All right. So, okay. One note before we start the new topic. I talked about how any tensor can be written in terms of its components, right? Locally. So it's like that, and times what? Right. So. Right, where these are local frame, and these are the dual frame. Right, and then decomposition like this exists for any tensor field on any vector bundle, so not necessarily tensor field on the manifold, right? So this would be the section of NRS power of some bundle, right? But now, if we talk about which we denote gamma RS of a bundle, right? If we talk about vector fields just on a manifold, that means they are sections of the TRS power of the tangent bundle of this manifold, right? So these are actually, all of these guys are tangent vector fields or one forms locally. And in that case, of course, we have the canonical frame, right, given by a local chart, local coordinates. So if we have local coordinates xi, then this gives me a local frame, which is d by, I denote it just di, or d by dxi, same thing. And then the dual frame, what's the notation for that? Dx. So then every tensor on a manifold, not on the vector bundle, usually, canonically usually represented specifically in this frame. And we've also defined d of a function. So if this is a scalar function on manifold, then d of that function is, again, projection 2 composed with f star, where f star is from Tm into r cross r, which is Tr. Exercise, check that this is actually d of xi, right? So exercise, check the d of xi as a function, then applied to, as a one form, which we proved last time that it's a one form, right? As a one form applied to dj will be delta ij, right? Then that would prove that d of xi equals dxi, right? Which is good. Yeah. Mm-hmm.
That'll be over C infinity of u, where
So that's good for our notation to make sure that it's consistent. Yep. All right. So new chapter, vector fields and Lie derivatives. First, let me define integral curves of a vector field. What would that be? Right, so let's say I have a vector field. So gamma of t defined on some interval on the real line is a integral curve of x if what? Right. What's the tangent? Gamma dot, yeah. And that should be equal to at what point? This is the defining equation for the integral curve. So, you know, it's a curve which is everywhere tangent to the vector field. Okay. Not also tangent, but the velocity is the same. Not only tangent, but the velocity is the same. Okay. So locally, you know, in coordinates, this is xi dot of t equals xi of x of t. So these are, in general, nonlinear ODs. Okay. All right.
Can we say anything about x like x?
All right. So that's the point of basically this definition. So again, x is a vector field. A flow box of x at some point p is a triple of a neighborhood u0, a real number a, and a map f, where u0 is an open neighborhood of p. A is just some positive number, well, or plus infinity. And f is a map from u0 times I a, where by this I mean the interval from minus a to a, into m. So it's a, you know, it's a function that depends on two things, on t and on on the point of the manifold. Oh yeah, good idea. Such that number one, for all p and u naught, the map gamma p of t, which is defined as f of p comma t, has to be what? So I want this to be the flow of the vector field. So if I fix p, this map should reproduce the integral curve of p, the one that goes through p, right? is an integral curve of x. And number 2, f f sub t, which means just f with a fixed t, defined by ft of p equals f of t. It must be a diffio onto its image. Which is, from solvability theorems of ODEs, general solvability theorems, we know that for sufficiently small time, that will be a diffeomorphism. Because, let me say that in more detail, maybe. So we have, integral curve. Any integral curve is defined by this system in local coordinates. X dot I of t is xi of t, and at the same time, xi at, let's say, 0 must be some given point. So analysis tells us that there exist local solutions, i.e. for small t. Local means for small t. And they depend smoothly on any, basically, any parameters of the system that enter smoothly into these equations. In particular, x naught I. What? Yeah, like these formulas, these coefficients, this in principle can depend on some parameter. If it depends on it smoothly, then the solutions of the system will also depend smoothly on that parameter. Right. But x naught I is special in that the differential of the solution at t equals 0 with respect to x naught is identity because it is supposed to be x naught, right? And that by the inverse function theorem, basically, or implicit function theorem, whatever it is. Yeah, that implies that for sufficiently small t, because x is close to x naught, this will continue being invertible, right? And so if we pick this flow box, this neighborhood u naught, and at the same time this number a small enough, this property will be satisfied, and the flow will be a diffeomorphism onto its image, right? Because the dependence on the parameter is invertible. Differential. Just differential with respect to x naught. Just a sort of a hand-wavy argument for why it depends non-singularly on x naught for small t. Okay. So, basically analysis tells us that these flow boxes always exist for at any point P for any smooth vector field. Right? So we have several properties of this flow map. First of all, flow at T1 plus T2 is the same as flow T1 combined with flow T2. You can think of these guys basically as evolution operators, right? Of some dynamical system described by the vector field. And therefore, because addition commutes, of course, this is also of T2. So therefore, it's an it's not really a group, but it's abelian. Yeah. Mhm. Yeah. What? Because T's are not allowed to be anything. So this equation even only makes sense as long as T1 plus T2 doesn't escape the interval I sub A. Okay, so on common domain, just like here, F minus T is Ft inverse, right? Also by uniqueness or from the previous. Obviously, F0 is identity. Any vector field has a flow box at any point. Any point, I should say, in the interior, right? If the manifold has a boundary, not necessarily. If the vector field points outside, pokes into the boundary, it doesn't have a flow at the boundary. And finally, this is going to be pretty important. If Ft is the flow of X, then Ft push forward applied to X is what? What if I push forward a vector field by its own flow? So think of an integral curve, and it's everywhere tangent, right? What the flow does, it moves the points on the curve along the curve, right? What is it going to do to the tangent vectors? Right. Yeah, that'll be X. How do you prove that? I mean, to prove that, we need to take a time derivative and get the same differential equation that we started with. Right. So d by dt, what does that give me? What happens if I apply the time derivative to this? So this is a differential with respect to p, right? So let me, basically, I want to take differential with respect to t off this differential with respect to p off f of p, my notation, p t, and then this differential was applied to x at p, right? What's that? Right, so these are independent variables. We can obviously commute these differentials. So this is going to be dp and then dt f p comma t, and then all of this applied to x of p, vector field. Now, what is dt of the flow? Right, by definition, right? F is just a bunch of integral curves depending on p. So with respect to t is just the integral curves. Therefore, that time derivative is all right. Okay. sorry, that's not a little wrong, right? Because I'm not taking the time derivative at t equals 0. This is, yeah, so this is actually x of f t of p, right? All right. And then x of p. Okay. How is that computed? What do?
X is precisely the differential of f t of p.
Right.
So we could write this chain rule
Isn't that what we did?
Yeah. Okay.
Right. So we want to prove that the result is what? What would that be? Yeah. We want to prove that this is 0. Hmm. So yeah, it's not actually 0, right? What's on the right-hand side here? Right, what this equality is actually supposed to mean is the following. It means ft star x, let's say computed at p, equals x of f t of p, right? That's what we want to show. So let's take a time derivative of the right-hand side now.
I think you mean f t star of x evaluated at p, not f t star x evaluated. You're pushing forward a vector at p.
I feel like that's the same thing.
So
Mm.
you could say you're pushing forward the whole tangent vector fields or tangent vectors. So I guess that's how you define the push forward the vector. Yeah.
Okay, so that, let's finish this here. Now we need to take the time derivative of this. So dt of x of t of p. Right. What's that? So again, right, this is going to be the differential of x taken at what point? Right, its argument. Right, dt of x, and then times acting on then the time derivative of ft, which is x of p. Not x of p, it's x of f of t of p. So acting on x of t of p. Right.
Yeah, but that's wait. Are we sure that's what that is? Because x is when you say d sub p of x in the line previous to that, you mean just like the derivative of its arguments, right? And then you evaluate it at
Uh,
I think that's the notations are inconsistent. Yeah, which is why I think that the left thing shouldn't be that. So it's like so you either evaluate the vector at p and then push it forward to f of f t of p,
Mhm.
or you push it forward and then evaluate at p. Those are two different things.
So you want to say this, yeah? I'll say that. Okay. So you want to, okay, so how does this change then? This is still this, right? This is still this, right? So this would, I should probably change the argument here, obviously. But this still doesn't change, right? This argument here. Let me think. So this, okay, it's easy to check, right? Whether it's right or not. A differential computed at point P should be always acting on the vector that sits at point P, right? So this makes sense because it's at x of P. This makes sense. This already doesn't make sense. So it's the vector, the time derivative of this is this. That is correct. But when I commuted the two differentials, I need to change the point at which I'm computing, right? Yeah. Mm. You're asking this? No, because time derivative of f of p at time t is a vector at p, right? So it's that. Sorry, it's it's a vector of ft of p. It's already evolved. Yeah. Okay, let's try that. Right. This is you want to say it's d ft of p x, right? Then acting on d at p of f, yeah, d at p of ft of p, and all of that on x of p, right? But now this acting on x of p is what we want to show basically equals x of f of t of p. So yeah. So that's the same equation that we're trying to show. How does this work? Should be more trivial. I'm pretty sure. Well, let's think about it. So all I need to show is that actually, so there's a statement of uniqueness, right, which says that X is the only vector field whose flow is any given flow, right? Ft. That's because Ft dot is X, right? Ft dot is X by definition. So we need to show that this vector field has the same integral curves as X itself, right? So let's apply this to a function. Let's apply this to a function. Okay. How's that defined? It's X applied to the pullback of that function by the vector field, right? Which is the same as X acting, by this I mean the Lie derivative, right? X acting on F of Ft of P, whatever the point is. Which is all I needed to show, right? Because we know this is an integral curve of X.
Isn't that just that?
I mean, basically, yeah.
No, that is literally just that.
Yeah. That's what happens when you don't write down the proof in the notes. Yeah. Because I'm remembering some similar proof from the future, and it's not the right one. Yeah. All right. All right. Sorry about that. So let me define this for a vector field X. I'm going to define this as the flow domain. It's a subset of in which order M cross R. So this is the maximal domain of the flow of X. Okay. In time and space. Well, it's always defined for some time at every point. So basically, it looks like this. If this is M and this is time, then the flow domain is going to be some neighborhood of M. Sorry, it's supposed to be symmetric by my definition, right? But this is going to be the flow domain of X. I mean, it could be infinite at some points, right? It could be infinity, whatever, infinitely wide. But it's going to look like that. And non-zero thickness at every point of M. So we call a vector field complete. Definition, X is called complete if its flow domain is all of this, i.e. it's defined for all time. Its flow is defined for all times. And here's an example, or two examples of non-complete vector fields. So first of all, let's take M equals the plane or the line minus 0. And the vector field is just going to be dx. It's just the constant vector field in that direction. So I have this point is not in the manifold, and my vector field points in that direction everywhere. Is its flow complete? Right, so f1 of the point minus 1, 0 is undefined, right? Therefore, incomplete. Another less trivial example is M is the real line, and the vector field is x squared dx. So we're solving the equation x dot equals what would be the solution with, let's say, x of 0 equals 0, right? So if you solve this, which I'm lazy, then x of t is 1 over 1 minus t. All right. At t equals 0, it's actually 1. Oh yeah, 0 doesn't go anywhere. So at t equals 1, it escapes to infinity, right? So the flow domain of the point 1 equals minus infinity to 1. I guess by my definition, it's minus 1 to 1. It has to be symmetric. So also incomplete. So maximal, yeah, for which the solutions exist, right? So incomplete vector fields are incomplete because their flows run into, basically fall off the manifold in finite time. Whether it's infinity or not is subjective, right? Because this could as well, you could easily call that infinity too. No, that's a theorem. Okay, so didn't use one word. So number one, there's a sort of a corollary. Let's say we have a vector field, and let's say its flow is fx. Let's say f is a map between two manifolds. Then the flow of f star x combined with f is f combined with the flow of x. Okay. Now the proof of this is to take a time derivative. So let's take the time derivative of the left-hand side. All right, what do we get? Chain rule. So I'm not going to write the arguments anymore. Because I mean, it's f star, okay? It's a differential of f, right? So it's f star combined with the time derivative of this dot x, which is, oh, sorry, x, which is f star combined with x, right? Which is what? Combined with x at which point? No, at which point am I computing x? ft, right? So combined with ft. Okay. What's that? So this is the vector field that I'm supposed to have here. Why am I getting confused with this? Right. Once again, this is x. Let me do f star x. Okay. F star x is the vector field that I want here. I want to say that this equals. Yeah, but it's computed at a different point. That's important, right? So I want to say that this is actually f star x at the point computed by f. But this thing, of course, is the time derivative of the flow of that thing. So it's time derivative of the flow of f star x composed with f. Yeah. All right. Got to be better with differential chain rules. Yeah. And of course, at t equals 0, the two sides are obviously equal to each other, so that's why this is sufficient. All right. Now, there's an important theorem, which is called uniform time lemma. Let's say we have a vector field, we have its flow domain D. If there exists an epsilon such that m times epsilon interval is included in the domain, i.e. the flow domain is epsilon thick everywhere, at least epsilon thick everywhere, then X is complete, right? So the proof is very simple. I'm not gonna even write this out, but let's say this is the time axis, and I find the point for which the flow is only defined up to some point B, right? Then I will look at the point B minus epsilon over 2, and the statement is that the flow exists for time epsilon for every point, right? Which means I'm supposed to be able to evolve B to this time, right? F epsilon applied to B will exist here, which contradicts the fact that the flow domain is the maximal set for which the flow is defined, right? And that's it. So, yeah. So even before compact corollary, if the support of the vector field is compact, then X is complete. because we can cover the set by a finite number of flow boxes. Each of those flow boxes has like an epsilon of its own assigned to it. Out of those, I can pick the minimal one. For that epsilon, I will have a global flow. And outside of that set, the flow is just identity everywhere. Okay. And in particular, on a compact manifold, all vector fields are complete. All right. Yeah. Oh, I epsilon, yeah, minus epsilon. Mm-hmm.
We should be using epsilon.
Mm.
Can't flip by epsilon. We can only flip by a little less than epsilon. Yeah, it's. Yeah, we have to do that. We have to apply f epsilon.
Yeah. So B, so I'm just assuming X is not complete, right? Then for some point on the manifold, the flow exists only up to a point B, right? Like the boundary of the flow domain. So I'm assuming there exists a B, which means incompleteness. And then I get this contradiction. So therefore B doesn't exist, and therefore X is complete. Okay. This is called escape lemma. It's just the following. If gamma integral curve of X cannot be extended to time greater than B, then T, G gamma, then the image of any interval that comes right up to B is not contained in any compact set. Okay. Not exactly. But if you assume that it is contained in a compact set, you can take a sequence that converges to B and get a contradiction out of that with the with the assumption that gamma cannot be extended. I will skip. It's pretty simple proof. Just don't want to spend too much time here. Then there's something called, I will not even really state, but there's something called the flow out lemma, which is the following. If I have, so first of all, there's a definition of a flow out. If you have an embedded submanifold in M, and you have a vector field, I don't know, such that it's nowhere parallel to S, i.e., x of p does not belong to TS for any p in S. Right. Right. then and D is the flow domain of X. Then phi is the flow of X restricted to the set, basically to S. I mean, S cross whatever time exists in the original flow, right? Just the flow restricted to S. This is called the flow out of S. And of course, it depends on the vector field, but that's a secondary thing. So the lemma says that this flow applied to a neighborhood which is sufficiently thin in delta. So this is the set S cross I mean, sure, a delta. In principle, delta could be a function of the point on S, but you know, if delta is sufficiently small, then this is an immersion into M. Right. So basically, this says if this is my S, and I pick some vector field that pierces S, right, is nowhere parallel, then the flow out along that vector field will create like a neighborhood, and the flow out is going to be non-singular, meaning that this integral curve will not intersect this one. Right.
But the thickness of this
Yeah. But if you pick basically there exists a delta, such a sufficiently small delta, such that this flow out produces like a neighborhood of S, right? Of dimension 1 higher than S. It's not really a neighborhood of S, right? It's just something of dimension 1 higher. No, it's lemma. Wait, lemma. Yeah. So lemma. Yeah. And also phi star applied to d by dt. Phi is a function of t, right? So I can apply it to d by dt, which lives on the real line of time. That of course is going to be x itself, right? So x measures time, obviously, by definition of the flow, I guess. Anyway, so this construction, and also if the codimension of S is 1, then this thing is actually embedded into M. So in particular, flow outs of the boundary of a manifold are embedded submanifolds. Okay, so I will also skip the proof. It's pretty simple, but I'm not going to use this much. And so this thing is called a collar. Right, so let's say I have my manifold M with the boundary. DM. Okay. So this, the flow out that I get along any vector field transversal to the boundary is called the collar of the manifold. And it's open. Okay. So this collar is going to be diffeomorphic to this semi-open interval times okay. And this lets us do at least one interesting thing, which is gluing of manifolds. Okay. So let's say I have M and N such that their boundaries are the same, meaning diffeomorphic. And this is diffeo. right? So boundaries have to be the same. Then can glue along H. And the way this is done is you take these two boundaries. Okay, so first of all, in the topological category, you would have just glued them at the boundary, right? Identify points in the boundary along H, that's it. You don't have to do anything else. The topology glues itself by definition of the quotient topology, right? With smooth structures, it's more tricky. You have to glue more than just the boundary. This is why we need flow outs. So you flow out to some distance, and then you glue this entire neighborhood to the collar of the other manifold, right? Because these two are diffeomorphic, we know. Okay, and then that way you can match the smooth structures and produce a smooth manifold. Mm-hmm. I mean, you can throw out the boundary. You can get rid of the boundary, right? Subtract the boundary off and glue the rest. The procedure is described in detail in the notes. I just don't really need it much. So you can glue. You can also do something that's called a connected sum of manifolds. All of this, by the way, belongs to the subject that's called surgery in topology and geometry. So connected sum is denoted M hashtag M2. So this is M1 prime glued along H1, H2 minus 1, M2 prime. Where M1 prime is M1 minus U1, and this is a coordinate ball. So we cut a ball out of M1 and M2 prime, similar thing. And H1 is a diffeomorphism from the boundary of U1 to whatever dimension, Sn, the sphere, the boundary of the ball. And this is a diffeomorphism. And similarly, H2 is from the boundary of that. Okay. And all we do is we cut out these two holes and we glue their boundaries to each other as before. And we get a new, yep. So for instance, if I have a manifold like that, a torus here and a torus here, the result, what actually happens is I'm making a hole here and I'm connecting a tube between them, right, in a smooth way. That's what this procedure does. Okay. What? I'm gluing smoothly here, so. Yeah. So that's that. And also a special example of this is D of M. It's just M glued to itself along its boundary. This is called the double of M. And there's a statement that if X is parallel to the boundary of some subset of the manifold, then the flow of X leaves D invariant. Maps D into itself. Kind of a simple statement. And a statement that follows from the construction of the double is if X is parallel to the boundary of the manifold, then the flow box existence applies to X at the boundary 2, right? Because remember, in general, it was true only in the interior of the manifold. But here it's true at the boundary, because the way this works is you can extend x to the double of m, which you can do consistently because it's parallel to the boundary, right? So it's not, when you make a copy of m on the other side, it's not ambiguous what x is at the boundary, right? So we have our manifold m. Yeah, the second copy of m here. This is dm. Because our vector field was parallel at the boundary, I can extend it smoothly to the double, right? Then the flow box theorem applies to the double, to x on the double. Then I restrict back to m. I get my statement, right? All right. And finally, probably the most important theorem about vector fields for a while is this. Oh, also, by the way, in principle, you can consider time-dependent vector fields in the same way. Right, but vector fields that depend on time explicitly also. Then their flows will depend on 2 times, like evolution operators in time-dependent systems, right? They will depend on t initial and t final, and they will not form an abelian group anymore. And all of the same results pretty much apply there too. Okay, so the theorem is called rectification theorem. Okay, it says the following: if I have vector field and it's not 0 at point P, then there exists a local chart u phi at P such that its slice S given by P and U such that the first component of P equals 0, the first coordinate of P equals 0, so just literally the coordinate slice, is diffio to Sm minus 1. If that was a coordinate ball, then of course it's going to be diffio to Sm minus 1. Secondly, x at P does not belong to the tangent space of this slice, so it's transversal. Right? We can already change the coordinates in such a way that it's transversal to that slice. And finally, x equals d1 on u. Right? This is the main result. So you can choose coordinates in which x is just 1, 0, 0, 0, 0. Not 0. Oh, I'm sorry about that. Yeah. Okay. So we can always pick local coordinates in which x is 1, 0, 0, 0. What local coordinates would that be? Proper time. Yeah. So basically, first of all, you can always pick such an S, like this should be more or less obvious. Then we do flow out of S along X, right? So flow out of S along X. And the flow f sub t of x of S, where this is a parameter on the sphere. This should actually be ball, right? Why is that here? Yeah, it should be ball. Yeah. So this parameterizes the points of of the flow applied to the points of my ball, right? Actually, of some domain, on which that's defined, which is a subset of the ball, which is going to be an embedded submanifold of M by dimension counting. Codimension is 1, right? So I stated before that flowouts like that are embedded. And this parameterization itself, you can check that it's a diffeomorphism. So it's a one-to-one parameterization. And then time, you can use time as one of the coordinates to generate the remaining coordinate transversal to S, basically. And then obviously X is going to be D1. But the basic idea is, so the local chart specifically is going to be S comma T, and psi of that ft of X of S. And chart, that's just a definition of some function, right? Which goes from ball and time into our manifold. And then the chart that we are looking for is going to be just the inverse of this thing. And then X is going to be dt. It's a flow, right? These are all diffeomorphisms. That's a flow. Okay. So rectification theorem, pretty useful. So this means that there always exist coordinates in which the integral curve equations become linear, right? In fact, totally trivial. So my statement that integral curve equations are nonlinear ODEs in general means that, to solve that ODE means to find the change of coordinates in which it becomes linear, right? So actually, nonlinear is essential to the fact that it's a non-trivial equation, right? Okay. All right. So next topic, vector fields as differential operators. So we've defined Lie derivatives, and we have this property that Lie derivative along the push forward of a vector field of the push forward of some scalar function is the same as the push forward of the Lie derivative along x of that function, right? For any diffeomorphism of manifolds. So related property is that Lie derivatives are local, which means that the Lie derivative of x restricted to some open set U of a function restricted to the open set U is the same as this. Right? That's trivial. So eventually we want to show that the Lie derivatives are the same as derivations on the algebra functions on the manifold. Okay. We've discussed that before for just separate tangent vectors at points. But here, let me define derivations on the algebra functions now. So we work in the smooth category. Here I'm big F. No, but push forwards of vector fields only make sense when it's a diffeomorphism in general, because you might push forward two different values of the vector field to the same point otherwise, and that's a bad situation. It has to be a diffeomorphism. All right, so let A be just any algebra over a field K. a derivation on A is a k-linear map D from A into A, such that what? So yeah, just checking that there's nothing else. So for any product of two elements, it's supposed to be A times dB plus B times D. Right. Actually, if the algebra is not commutative, then so the space of all derivations is called derivations of A, and this is a Lie algebra with D1 comma D2 acting on A is defined as, of course, D1 D2 minus D2 D1. Okay. What's that? You mean that this is an algebra of operators? Sure. Yeah, it's an associative algebra. Sure. But this is a much more non-trivial statement. The fact that when you apply a commutator of two derivations, that still satisfies the Leibniz rule. Right? I mean, it's a trivial exercise that you can do on your own, but it's still a non-trivial statement in the end. So if you have an if you have an algebra and a distinguished derivation on it that is special to you somehow, then that algebra is called differential algebra. So it's an algebra with a derivation on it. All right. So we know that the Lie derivative is a derivation on C infinity. Right. Because it satisfies the Leibniz rule. And eventually, I want to go in the opposite direction and prove that every derivation on C infinity is a Lie derivative for some vector field. Also, any derivation on C infinity satisfies d of 1 is 0. Why? Of the constant. So even easier, d of 1 is d of 1 times 1, right, which is d of 1 plus d of 1 by the Leibniz rule. Okay. And also, the set of all Lie derivatives. Lie derivatives is a C infinity module. C infinity module. Right, because some scalar function times the Lie derivative is the same as the Lie derivative with respect to f times x. Okay, that we know. All right, so here's the theorem. The space of Lie derivatives Lx is isomorphic to the space of vector fields on M as C infinity modules. So not just as vector fields, but also as C infinity modules. All right. So in particular, the Lie derivative is 0 as an operator if and only if the vector field is 0. All right. Is this obvious or not? Yeah, let's just construct an isomorphism, right? So if I have a vector field, obviously I can get a Lie derivative. If I have a Lie derivative, how do I get the vector field back out of it?
Or do you mean if you have a derivation on C infinity?
Lie derivative. So I already know that it's a Lie derivative of x, right?
Yeah, exactly.
So it's a trivial,
trivial.
right? This is an empty statement, right? Because it's a renaming, right? There's nothing else. Okay. This is so this is less trivial, right? But basically, we know that first of all, it's enough to check at one point. At one point, we can just act with x on an arbitrary one form at that point. If and for every element of TP star of M, there exists a function, local, doesn't matter, global function, such that the d of f at p equals alpha p, right? Equals this alpha. So then we can take this Lie derivative, act on this function f. This is supposed to be the same as x evaluated at dp of f, right, which is x of alpha p, which is 0. And we can prove this for every alpha p, which implies by definition of the tangent space that x is 0. Okay, so that's pretty simple. And the fact that they are isomorphic as C infinity modules was already written here. Okay. Now, on to the non-trivial theorem. The space of all R linear derivations on the algebra of functions is isomorphic to the space vector fields as a vector space. So, in particular, every derivation theta coincides with the Lie derivative of x along x for some x. Right. So basically, all we need to do is, given a theta, to construct a vector field out of it. Right. How would we do that?
we already defined our tangent spaces are the spaces of pointwise derivations, right?
Yeah, but I mean, one does not follow from the other.
Well, I mean,
Huh?
or would you just start with the fact that your tangent vectors at point are your pointwise derivations at
Mm, I'm not. It's not obviously clear to me how you would do that. But think of what derivations are locally, right? Locally, derivations do something to functions, satisfy the Leibniz rule, and we need to integrate whatever it does to that function to recover a vector field out of it. So let me explain what's going to happen. So first of all, theta is local. Theta is local because if I act with theta on this, where this is a bump, then the result is also going to be 0 outside of the support of chi, right? So that's what it means for it to be local. And it's local just from Leibniz rule, right? So let me choose chi bump that's equal to 1 around P and 0 outside some neighborhood V that includes P, right? And let's say H is a function such that H on V is 0. Okay. H on V is 0. This also implies that theta H on V is 0. Okay. Then theta on H. First of all, in general, H is going to equal 1 minus chi times H because their supports are disjoint or something. And theta of H of P, for a general point P, is going to be equal to theta of chi H plus 1 minus chi H of P. That's just an identity. But now I can expand this and get theta of 1 minus chi times H of P by Leibniz rule plus theta of H and then times 1 minus chi of P. Okay. But both of these are 0. Why? At a general point, right? But it's because their supports are basically disjoint, right? It's either this is 0 or that is 0, this or that. Right? So nowhere to go. Right. So that's basically the proof of locality of theta. All right. So let's pick a local chart. So phi goes from U to Rm, where this is some neighborhood of P. This is a chart. Let X be a coordinate, specific coordinate, new hat, and F be a function on M. Then phi star of F in of X, which is the local representative of F in coordinates X, right? Is going to be, we have this rule from formula from like first year calculus, that this equals its value at a plus the integrals of derivatives, right? So plus the integrals, the sum from 1 to m over xj minus aj times integral from 0 to 1 phi star f j, where by this I mean d by dxj, phi star xj, and then times a plus tx minus a dt. What's that? Yeah. So this is true on some neighborhood of this point A. So now we can simplify this to just stating that f of u equals f of p plus phi I of u minus a g I of u for some smooth functions gi. So some C infinity local functions, which are these integrals. Sorry, not integrals, these derivatives. Right. These xj is the same as phi I, definition of coordinates. Okay. Therefore, if I apply my theta to this function, I can use the Leibniz rule. This is constant. So I get gi of p theta phi I of p. That's it. Which is the same as dxi of phi star f. That's my gi. At a times theta phi I at b. Okay. Okay. What now? How do I construct the vector field that I'm looking for? So this is just my partial derivative of the local representative of the function, right? The coefficient in front of that is supposed to be the component of the vector field that I'm looking for. Right. This is supposed to be my component of xi, right? So define x by local representation. Xi at point u is theta ith coordinate of u. Right. So all we needed to do was just apply theta to the coordinate functions, and those are the components of the vector field we look for. Now, what do we need to check? Check what? Sure, but even before that, I defined x locally, right? Nobody said that this is going to glue into a global vector field, right? So we need to check that this definition of x is phi independent. So as a vector field, that it's independent of the local chart, and therefore that actually defines a global thing. But that's just because if I apply differentials, those differentials will commute with the theta. Yeah, you can check that by definition, by Leibniz rule definition of theta. Okay. Secondly, yeah, we need to check that this reproduces the derivation, the Lie derivative reproduces the derivation. So let's so local representative in the coordinate x, which is phi of u, of the Lie derivative of some function f is we take f, we compose it with phi inverse, take star at point x, compose it with x, right? That's how the Lie derivative is defined. Compose it with x hat, sorry, the local representative at x, right? That is going to be d by dxi of f circ phi inverse of x composed with, by definition of x, theta phi I, right, of u. But this is by chain rule, theta f of u.
Oh, okay. So by chain rule, assuming the form we have for data.
Mm. I mean, we had this formula before, right over there. We proved this formula. I thought. Yeah. So, yeah. Hence, theta equals x. That's what we needed to show. And uniqueness, maybe I forgot to state in the statement that this x is unique for the theta, right? And that follows from the fact that Lx equals 0 if and only if x is 0. And these are all linear objects. Okay. Okay, cool. So Lie derivatives are the same as vector fields, are the same as derivations on the algebra functions. Right. And now magical proposition that states that if I have two vector fields, then the commutator of two Lie derivatives is also a derivation on C infinity. And that's true just because it's true for any algebra of derivations, right? So nothing to prove. I mean, trivial exercise. But it is a very surprising, well, to somebody who's never seen this before, it should be surprising because this looks like a second order differential operator. When you act with it on a function, you expect to get some second derivatives out of it. But it turns out that the second derivatives cancel and only first derivatives remain. And first derivatives are a derivation and therefore a Lie derivative. Okay. So this leads us to the definition of Lie derivatives of vector fields. So if I have two vector fields, then define this thing, which is also denoted the Lie derivative of y along x by the condition that the Lie derivative along this object of functions equals to the commutator of that, right? So Lie derivative of the commutator of x and y must be equal to the commutator of Lie derivatives, right? And because we already know it's a derivation, this defines a vector field. And without this theorem, we wouldn't have been able to say that. Right?
So in no sense can we say that the Lie derivative of vector fields is some kind of different or derivation on vector fields that don't have an algebraic.
no, I mean, no, you have to go to all tensors then, and we'll see it's a differential operator. It's a differential operator on tensor algebra. Right. So in local, if you write this out in local coordinates, then you'll get the jth component of this vector field is xi di by j minus the other way around. So yi d I xj. Okay. So here are the main properties of these Lie derivatives. Number one, they are local and natural with respect to diffeomorphisms, which means something similar to what we had for Lie derivatives of functions. The push forward of x comma y is the same as the commutative push forwards. That's number one. Number two, Lx is a derivation. So you needed to specify on which algebra, right? Okay, so it is a derivation on the Lie algebra of vector fields, which means that the Lie derivative of y comma z, right? I could have written this as a double bracket, but let me write it this way, is equal to the Lie derivative y comma z plus y comma Lie derivative of z. Right. That's literally derivation with respect to this multiplication operation. Yeah, this is just the Jacobi. Well, on the, okay, right, therefore Lie. Yeah. Yeah, it's a general statement. Okay. Number three, Lx is also a derivation on C infinity of M tensor vector fields on M, which means that it satisfies the mixed Leibniz rule. So Lx of F tensor a vector field. Tensor is really just multiplication, a scalar multiplication, right? Is Lxf times y plus f times Lxy. That's what that means, right? Doesn't follow from anything so far. No, obviously, it doesn't follow. So we need to prove that. Or equivalently, L sub fx of y equals f times Lxy plus Lxf times y. So we could have multiplied y by f or x by f. But these formulas are slightly different in spirit, even though they're the same because the commutator is anti-symmetric. So multiplying y by f or x by f is basically the same thing for this general formula. But this is different in spirit because if you remember how covariant derivatives work, then the covariant derivative with respect to a vector field is the same as multiplied by a function is the same as that function multiplied by the covariant derivative with respect to the vector field. That's it. This derivative does not act on the function, which justifies the notation xi nabla I, which we use for covariant derivatives acting on whatever. Here, that's not true, right? This turns out to act on f, and that's why Lie derivatives are not covariant derivatives, are not special cases of covariant derivatives. Because the derivative acts on both symmetrically on both objects. It's not just one vector field that acts on the second one. All right. So the proof is pretty easy. So to prove these first two, for instance, you just act on an arbitrary function and just unwrap the definitions of Lie derivatives, commute the push forwards with whatever differentials you have in there, get the necessary identities. It's pretty boring. Number two is just a general, doesn't have anything to do with vectors, right? It's just a general Lie algebra stuff. So you expand both sides explicitly. By acting on some function, you get the same on both sides. Okay. So the only non-trivial thing is 3, which is, so we do this, and let's act with this vector field on a function g, and open this. So this is Lie with respect to x of Lie along fy of g, and then minus lfy lx g, right? Commutator. Now, this thing is a Lie derivative acting on the function, so f can be pulled out, right? So this f can be put over there. Then this is a function times a function, and the Lie derivative acting on a function. So Leibniz rule. So this equals lxf times lyg plus f lx lyg, and then minus f times ly lxg. Okay. But this you can compactify into lx y lx with f y plus f commutator x y g. Does that work? Yep. Right. That's the commutator, and that's the Leibniz rule that I wanted to prove. That this equals that. Okay. So that's it. So that's pretty cool, right? We have a Lie derivatives. We now can act on functions and on vector fields. They are both derivations on the corresponding algebras, algebra of functions and Lie algebra of vector fields. And moreover, they are consistent with each other, right? Through this mixed Leibniz rule. And it turns out that all of this is enough now to automatically extend Lie derivatives to arbitrary tensors. And that's sort of the statement of the theorem. Let me just prove this theorem. It's very quick, and we'll finish there. So let me define tensor differential operators. So what do we mean by a differential operator acting on tensors? And this is going to be a useful definition for me because we will later refer to it when talking about covariant derivatives, I guess, in the Riemannian. Well, I don't know. Anyway, it's a useful definition. So gamma of m was the entire algebra of tensor fields on M, right, of any rank. Then D is going to be called a tensor differential operator if it's a collection of maps DRS of U acting on tensors of rank RS, local tensors on every neighborhood U, and into itself. Okay. In a way that such that it's consistent across the different ranks, meaning Leibniz rule with respect to what? Tensor product. Okay, so uh, so for each U open subset of M, such that number one, and I'm gonna denote these all collectively by just D, not writing RS. So D is a tensor derivation with respect to tensor product. So Leibniz rule, right? Number two, D is local, meaning that the D of any tensor restricted to U is the same as D of that tensor restricted to U. Okay. Where this is the D acting on all M, and this is the D on U, right? I'm just using the collective name for D. And finally, the differential operator acting on the Kronecker tensor, which is just the identity on the tangent bundle. I guess I haven't, have I defined this before? This would have been a useful example when I introduced tensors, right? But this is the identity on TM. That's the Kronecker tensor. It's supposed to be 0. Yeah, I mean, by the way, notice that we don't require the naturality that this commute with push-forwards by diffeomorphisms, which was true for Lie derivatives, but I don't want to require this in general because, for instance, for covariant derivatives, it's not true. So we don't require that. Okay, so here's the theorem. It's pretty neat. General theorem by Wilmore. And Wilmore. It says the following. A collection of local tensor derivations E sub U on C infinity of U and F sub U on the Lie algebra of vector fields on U for every U open subset of M, which agree with each other via the mixed Leibniz rule. For every U open subset of M, determines a unique tensor differential operator, D on the entire tensor algebra, such that D on C infinity is the same as E, and D on vector fields the same as F. Okay. And the proof is easy. Here's the idea. So locally, every okay, so the statement that I want to prove is that D can be explicitly expressed in terms of E and F only, and the formula for that expression is uniquely determined by the definition of D. So that formula, it has to be unique because that formula follows from its definition. Okay. So let's try it. Locally, any T is Q with some indices of EI1, EIR, alpha J1, alpha JS. Okay. So by Leibniz rule, Leibniz D applied to this tensor, because it satisfies Leibniz, is going to be D of the components, and then times these guys, right? Then plus the components times D of these vector fields, right? Sum over I, then plus sum over J. And here you'll have D alpha J 1, right? So by Leibniz rule, just act on every one of them. Now, we know what these are, and we know what this is because it's a function. This is a vector field. We don't know what this is because this is a one form, and that's not given to us, right? But the claim is that we know what that is uniquely from definition of D, right? So because D acting on the Kronecker tensor is 0, and the Kronecker tensor locally is just EJ tensor alpha J summed over J, we have 0 equals D EJ tensor alpha J plus EJ tensor D alpha J, right? And we need to extract this from there. How do we do that? How do I kill EJ? Act with alpha J, or alpha I, right? So contract, so yeah, so delta ij is alpha I of vj. Therefore, by contracting with alpha I, or actually EI turns out to be better, I guess. EI contract with EI, 0 equals FU acting on EI plus D alpha J EI EJ. Okay, and these are the components, right? So J, the ith component of that. The what's the? No, it's a one form, so it's a lower. Right? Yeah, the same indexes. Okay. So this defines the components of this guy. Okay, in that basis. And that's it, right? Therefore, D on X star is uniquely determined by this formula, and therefore D on the entire tensor algebra is uniquely determined by that formula, and that's it. It's the end of the proof, right? So now we use this formula. We use the tensor Leibniz rule to plus that to extend Lie derivatives to the entire tensor algebra, right? So definition: Lie derivative of tensors. The X acts on the tensor algebra by Wilmore. That's it. And there's an explicit formula, it's just by Leibniz rule, which I'm not going to write out, which basically states that the Lie derivative commutes with contractions. Right? That's the meaning of being a derivation with respect to tensor products. Right? Commutes with contractions. And the last property here, which gets automatically extended to all Lie derivatives of all tensors, is this push forward property. Right? How do you prove that? Well, you define an operator, define a new differential operator by the left-hand side, divide by f, and define this whole thing as d. So define d by dt is going to be f upper star of Lie derivative f star t f star t. Right. F star, sorry, x. Yep. And we know that this already coincides, right? So D already equals Lx on C infinity and on vector fields because we had this property for C infinity and vector fields. Therefore, on the entire tensor algebra is true by Wilmar, by uniqueness of this differential operator. Right? That's a pretty neat argument, right? So this is going to be a pretty important property for us in the future. But that's it for now. Next time we will finish Lie derivatives, discuss their geometric meaning. But next time is going to be in 2 weeks.
Is there anything in particular about the tensor algebra here, or could we just make extends to its subalgebras, like the exterior algebra? Or this would also automatically be true there.
I mean, we will have it for exterior algebras, but it's not immediately obvious that it maps that algebra into itself, right? So you have to be careful.